help doctors do their jobs better, or it might be used to help architects, or, for example, to help truck drivers. So we learn a lot and read a lot about self-driving cars in the news. But already on the roads, there are actually companies that are deploying devices to basically be following truck drivers as they drive and recognizing when they are, for example, distracted and alerting them. So these devices that are using AI to monitor truck drivers and to result in fewer collisions on the road, it's a very narrow application of the AI. The AI is not yet replacing the human. And that's our first stage of AI. And one way to think about how powerful this stage of AI is, even though it is just incorporation and just the first stage, is to think about comparing a horse and a car. So there are a lot of ways in which horses are actually superior to cars. So a horse can end up recognizing a route by itself. If you keep a bunch of horses and you treat them well and they're in a particular place and you've got male and female horses, you might end up with some self-replicating horses. You're gonna have some new ones. Whereas if you keep a bunch of cars in your garage, you're not gonna end up with any extra cars, right? And that said, to take a car from one point to another, if you've got a good road, is much more powerful than driving a horse, which is why our human society today has changed a lot from the time when we all rode horses. So, but cars, again, they're good at getting from point A to point B. They can't replace every bit of a horse, but they still have replaced the key way that humans would use horses. So I want to compare AI and what AI can do to the kinds of computers and kinds of computer programs we're all familiar with, whether or not we're using AI today. So I call what we have been doing up until now pre-AI software 1.0. And with software 1.0, what you do is you take a hard problem like getting to the moon, and you break that problem down into small problems, and you create algorithms to solve those problems, and then you invest a lot in your system's architecture to take those problems and weave them together in a full-fledged solution. And software 1.0 is pretty incredible. Not only has it gotten us to the moon, but we have automated many systems and processes, and we do a whole lot online and with computers that do not rely on AI. And we do it with actually much less computational power. So we got from the Earth to the moon with computers that were less powerful than the computer we all have in our iPhone. And the computers that we have in our iPhone, they're very powerful, but they're still not powerful enough to run cutting edge AI. So AI, narrow AI, I call software 2.0. And for software 2.0, there's three key inputs. There's data, computational power, and your algorithms. And a lot of people spend a lot of time focusing on the algorithms or the models. And they want to find some way of creating a new, better model. But when it comes to bringing your AI into business, it's not actually about your algorithm. So Google makes available some of the most powerful algorithms around today for free on TensorFlow Zoo. And so if you want the state-of-the-art model, you can get that for free. But what you can't get for free is data, particularly data where you've trained the data to support the machine in being able to understand and interpret that data. And then the other piece that's really key for a successful machine learning application is the computational power. Because the methods that are used in software 2.0 in weak AI use enormous amounts of computational power. And let me explain why that is. So our innovation when it comes to software 2.0 is the ability to have a deep neural network. You have inputs, those are the X's on the slide, and then you have your neural network. And you can see you have these various layers, and you ultimately get to the output. And in software 1.0, if you were, for example, going to have a software 1.0 program that would recognize features in a sonogram and be able to support a doctor in reading the sonogram, you would have to take that problem of how do you find the features that are relevant, that are what a doctor would find, and you would decode that into lots of little pieces. And then you would find small algorithms to solve those different pieces and take your systems architecture to build up a solution. And the solution would be, it would take less computational power, and you wouldn't need the training data the way you need with AI. But this kind of software 1.0 is going to be brittle, and it could potentially help a doctor, but it's not going to be nearly as dynamic as software 2.0 or AI. So with software 2.0, what you have is instead of basically as humans figuring out what are the features that are important for the computer and then encoding them into algorithms and building that systems architecture, you label the relevant features. So you can see on the slide the various color blocks. Those color blocks that are there on the slide, that's the image being labeled. And so those blocks are going to be recognized by the computer. And humans are actually going to be labeling the data. So you might take a radiologist and have them start labeling slides. And you're going to then feed those labeled slides into your neural network, and you're going to train your neural network. And then basically what you do is you take new data and you test it. And you see, okay, we put in these new inputs. What does the neural network come out with? And that's going to be when you're deploying your model. And so the key part here is the labeled training data. I like to call labeled training data the new gold, because getting access to that data is expensive and hard. This is part of why we see some incredible advances in AI taking place not in startups, but in large companies, where they actually have access to proprietary data sets. And it's not just enough to just have the data. You have to find a way to structure the data. So if you think about taking information and putting it into Excel, how many of you here use Excel? Everybody's used Excel. So you take data, you take information, when you put it into Excel, all of a sudden you can run operations on that data. Excel structures your data. You now have a way to interpret and interact with the data in a new way that makes it very easy to run programs. And similarly, when it comes to our proprietary data sets in industry, we have to label that data so that our machine learning algorithms can recognize the relevant features of the data and come out with the results that we can deploy in production. And so now we have had in just the past 18 to 24 months a pretty incredible development in access to tools to help us to train data without needing coding. And so here you can actually see what it looks like to train data. So you've got some geospatial imagery data, and that data is being labeled. And then you've got solar panels. These are defects on solar panels that are being labeled. And you can have humans do that labeling from anywhere in the world, and they don't need to know how to code. So if we think again about software 1.0 versus software 2.0, in software 1.0, you need people who know how to code to figure out how to take the relevant features of the data and build out your systems architecture to come up with a solution to your problem. But with AI, what you do today is you can use these tools to label data. You label lots and lots of data. You feed that into the models, and then your AI models can start to provide better results on new data without you even necessarily fully understanding why and how they're doing that. So I'm going to talk to you a bit more about computer vision in particular. So computer vision is teaching machines how to see. And when it comes to software 2.0 or AI, it's not just computer vision. We can also create AI that can hear. People are working on creating AI that can speak. Any cognitive task that a human can do, we can use these AI methods to teach AI how to do those tasks. But for computer vision, what we're doing in particular is we're teaching machines how to see. So one example of very advanced and powerful computer vision is Facebook's facial recognition. And so Facebook's facial recognition has gotten so powerful because part of the Facebook business model is we have all trained the Facebook data. So when we upload photos to Facebook or Instagram and we tag those photos, we're actually teaching Facebook's AI algorithms how to see. And with computer vision, what's interesting is the features that matter for recognizing a face are very different when it comes to computer vision that works than you might think as a human. So it's not about eye color. It's not what we humans might point out, but it's actually about the distance of the various facial features. So you can kind of see these dots on this image. These are the aspects of facial features that are extremely relevant for facial recognition programs.